one of the most valuable things I think in working with number systems is just understanding the basics of how they work. So I'm gonna go straight to base 10, which is what we're used to. We have the digits 0 through 9, the integers 0 through 9. Now, we know that we can describe anything in terms of quantities between 0 and 9. We can use those digits to represent quantities. So we don't have, there is no digit beyond 9. Every digit in every number, even if you take a look at the number 962, every digit is between 0 and 9. But it turns out that we know that the place value is of significance, where that number is within its place value, the first, the second, or the third place value. And we know that as we move to the left on a place value, that describes a larger and larger quantity. So I wanted to start off with this idea that let's suppose that I have 9 of something, and to that I want to add 3. Well, I don't have a number to represent that. Now, we all have learned that we can do this, we write down a 2, we carry a 1, and then we put a 0 down there, and we add 1 plus 0, and we get the digits 1 and 2, which we say 12, but which consists only of the digits 0 through 9. But what is really going on if we analyze 9 plus 3? So let me just draw 9 little squares, 5, 6, 7, 8, 9, and then I have 3 more than that. Okay. Well, because once I add 1 to 9, I no longer have a digit for it. The way we often think about it is we group together every set of 9 plus 1. So what I'm doing here is I'm grouping together a set of 9 plus 1. I'm not calling it 10 because 10 is technically not a digit, but it's one grouping of 9 plus 1. Okay? So what I'm going to think about here is this is one grouping of 9 plus 1. And what I'm going to do is I'm going to, rather than keep track of it in the place value of what we call the ones place value, which could be any number between 0 and 9, what I'm going to do here is I'm going to create a second digit, and I'm going to say this is the number of groupings of 9 plus 1. Okay, so I have in 9 plus 3, I have one full grouping that I could create of 9 plus 1, but then I see that I have this residual, this residue of these extra 2 units. Well, representing 2 units, I probably shouldn't box it in because it's not really a grouping, but I have 2 individual units which I can represent in what we call the number of groupings of 1. Okay, this is the number of groupings of 1. Okay, so this is what we call the number 12, but it's really comprised of the digits 1 and 2. Now I can do this for any sequence of numbers. I can add 14, and I'm sorry, not 14. Well, we could say 14 now, right? 14 would mean that I have one full grouping of 9 plus 1. So I have one full grouping of 9 plus 1. That's what this digit represents. And then I have 4 more individual units which can be represented in my first digit in the first place. And let's say I add something to it like 1, 3. Okay, 1, 3 would be, again, one grouping of 9 plus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 1. I have one full grouping of 9 plus 1. And then I have 3 more individual units. Well, if I analyze this and I ask myself, how do I add these together? Well, now I have to ask, how many groupings of 9 plus 1 do I have? I have 2 groupings of 9 plus 1, which is why we end up adding those digits. We usually start here, right? We usually start in the ones place just to make sure that we don't actually end up with one more grouping of 9 plus 1. Well, we don't, because we had 1, 2, 3, 4, 5, 6, 7, which we can actually still count using the digits 0 through 9. This same type of logic applies whenever we have a number like, I'm going to say 9, 7, and we add to it something like 4. Okay? Well, what I have here, and I'm not going to draw out all of the groupings of 9 plus 1, but I have 9 groupings, 4, 5, 6, 7, 8, 9 groupings of 9 plus 1. I'm not going to put the little squares in there. And then I have this number right here has 7 individual, 2, 3, 4, 5, 6, 7, or 7 singlets. And then this, we're adding 4 more singlets to it. 1, 2, 3, 4. Okay, well that gives me a new grouping of 9 plus 1. And that gives me a new grouping of 9 plus 1 right there. So now I have 3 individual units. Okay, so that's where we would, oh, not 3 individual units. 1, 2, 3, 4, 5, 6, 7, 8, excuse me, 9 plus 1. There we go. We have 1 individual unit. We have 1 individual unit. Here's where we would kind of carry the 1, right? Imagine carrying the 1. What are we doing here? Well, now we had 9 groupings of 9 plus 1, but now we have 9 plus 1 groupings of 9 plus 1. We have 9 plus 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 1. We have 9 plus 1 groupings of 9 plus 1, and that's too many for me to be able to keep track in this place value. So what I'm going to need to do is create a new digit that keeps track of the number of 9 plus 1 groupings of 9 plus 1. So here's what I'm suggesting. This gets kind of weird as you go further, but here is what I'm going to do is I'm going to group or box in my 9 plus 1 groupings of 9 plus 1. Now, this is what we would often think about as the number of 100s, okay? The number of 100s. Well, I have one 9 plus 1 grouping of 9 plus 1s, okay? This box represents 9 plus 1 groupings of 9 plus 1. Each of these sticks contains 9 plus 1, and I have 9 plus 1 of them. Now notice that after I box that in, that all I have left is oops, I didn't count for those guys there. All I have left is this one individual singlet. I don't have any just 9 plus 1s left over outside of that purple box. So what I actually have here is 0. So this is the number 101, as we know. But what it means is that I have 1 singlet. I have 0, what we would call 10s. Let's use that phrase now because it gets weird saying 9 plus 1s. I have 0 10s, and then I have 1 10 multiple of 10. I have 10 groupings of 10, which is the number of 100. So that's where we get place value from. That's where place value comes from, and that's why we carry 1s like we do, and we carry a 1 here as well. So this is where, I'm jumping back over here, 101. This is what we would call the number of 1s, the number of 10s, and the number of 10 squareds, okay, or 100s. If you think about it, it's 10 multiples of 10, so 10 squareds. And then this is the number of thousands, which is the number of 10 cubes, and so on and so forth. So it gets pretty interesting, because now we have the same type of logic to any base number system we want. Suppose you visit a planet in which the residents have 5 fingers. How would you explain to them that you need $13 worth of their currency? So 5 fingers, we're in what we call base 5, and base 5 is only going to have 5 numbers, 0, 1, 2, 3, 4. It doesn't actually include the number 5 because we have to represent a quantity that indicates an absence, and so that is where 0 takes that slot. So how would we talk about $13? Well, if I represent 13 in our base number system, what we know is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We know what that means is that we can form one group of 10 and then 3 singlets left over. So I can box these in like this, and then I have these 3 singlets left over. I have 1 grouping of 10 and then 3 groupings of 1. Okay, but I want to explain this to somebody who has 5 fingers. So every time, not when they get to 9 plus 1, but when they get to 4 plus 1, they have to have a new place value for it. This digit can be anywhere between 0 and 4. this digit can be anywhere between 0 and 4. So once I max out this digit, right, 1, 2, 3, 4, and I get one more in there, okay, well that's one grouping of 4 plus 1. So that's what this digit is going to keep track of. Now I'll do it again. 1, 2, 3, 4 plus 1. That's two groupings. I have two groupings of 4 plus 1, and then I have 1, 2, 3 additional single units. So every time I overflow, every time I need to move to a next number, I'm going to have to use the next place value to keep track of how many groupings I have. So the number 2, 3 is what we would call base 5, and sometimes you would see this written as 23 or 2, 3 base 5. You should say 23 because 23 is an integer, and this is in a different base system. So we would just say that this is the number 2, 3. Now we can do the same thing when we add as we do with how we treat addition in integers. Let's say I had that number 2, 3 in base 5, but then I wanted to increase that by say $4. Okay, base 5, $4. So let's say that both of these numbers are in base 5. Base 5. We're not going to actually do anything with that subscript 5. I'm just indicating that we're not adding 23 plus 4. We're adding 2, 3 in base 5, which is 13 in base 10, with 4 in base 5, which is actually 4 in base 10 as well. Okay, so how do we add these? Well, first of all, we know that anytime we exceed 4, that we need to have a carryover. So this is kind of weird thinking, but 3 plus 4 means that I have one grouping of 4 plus 1, okay, but then I have 2 units left over, right? So 3 plus 4, let's think about this, let's imagine this. I have 3 singlets and 4 more singlets, and whenever I get 4 plus 1 of them, whenever I get 5 in other words, that has to create a carryover. I have one grouping of 5, and so this column is going to keep track of the number of those groupings of 5. And then what do I have left over after that? I have 2 individual units. That's where I get my 2, and that 1 is a carryover into the next column. So 1 plus 2 is 3. That's still a valid number in base 5. And so oddly enough, you add 2, 3 plus 4. In our mind, we expect 2, 7, but it's actually 3, 2 because of the way we overflow in base 5. Similarly, let's say we added 2, 3 in base 5 to something like 2, 4 in base 5. So what are we saying here? Well, we have 3 singlets, 1, 2, 3, and 4 more singlets, 1, 2, 3, 4. Okay, we can form one group of 5 out of that right there. One group of 5. That's going to be our carryover. And then I have 2 singlets left over. So nothing new there. That's the same thing we encountered in this situation. 2 plus 2 is good, right? 2 plus 2 is fine. That's how many groupings of 5 I have. I have 2 more groupings of 5. But now I have 5 groupings of 5. I'll just say 5 groups of 5. Well, I don't have the number 5, right? So now I have to do another carryover. Well, 2 plus 2, I have basically 5 of these, and this next digit, so I'll write down 0 anytime I exceed 4, and now I'll carry 1 over here and treat these as zeros, which gives me one grouping of what? Well, one grouping of 5 by 5. One grouping of 5 by 5. So that means 2, 3, 4, 5. I have that one there. I have 3 more groupings of, I'll just draw it like this. And so that means that I have 5 groupings of 5, right? And I have one of those. One 5 grouping of 5. Weird thing to say. So in terms of place value, this represents the number of 5 to the zeros. This is the number of 5 to the first that I have. This is the number of 5 squares that I have. And before you know it, we start to develop an algorithm without actually doing any formal mathematics at all, just understanding that once we exceed the largest number in our base system, we need to carry that over. So base 10 is the perfect example of that, but it's going to be a little bit harder to get used to, primarily because of the fact that we always add to 10 before we carry over. But the strange thing here is whenever you add numbers like this, it's after 5 that you carry over. Let's do another example. Let's say 33 in base 7 plus 22 in base 7. Let's go 26 in base 7. Okay, so anytime I reach 7, I have to have a carryover. So 3 plus 6 is the same thing as 7 plus 2. So I have one group of 7 in there. That actually is, think about it as 9, but then I can't go up to 9, I can only go up to 7, so that means I have 2 units left over. Again, you could do 1, 2, 3, 1, 2, 3, 4, 5, 6. So this is going to give me 7 units right there. I have one grouping of 7. Okay, that's what that next digit place value keeps track of. And then I have 2 singlets. So that's where we carry the 1. 3 plus 2 is 5, which is still a valid number in base 7. 5 plus 1 is 6. That's still a valid number in base 7. So oddly enough, 3, 3 in base 7 plus 2, 6 in base 7 is 6, 2 in base 7. This is much of the logic that we're going to be using in actually working with the algorithms in our next